Raring to go again. Let's remember where we were. At the end of the last lecture, what we derived was the action for a spinor field. And we really derived this. Remember, what we did was we looked for representations of the Lorentz group. We found a new representation, the spinor representation. We introduced a field. This is a 4-index complex object called a Dirac spinor. And this was defined such that it transformed in this particular way under the Lorentz transformation. And then we worked quite hard to figure out how we could write down a real action which was Lorentz invariant. Okay? And this is what we came up with. Yeah?
Before we had treated the field and its complex conjugate as independent variables in a lot of contexts, do we treat the field and its Dirac conjugate?
Absolutely, although it doesn't matter in that context, because if you treat the field and the Dirac conjugate or the complex conjugate as independent, it's just going to be an overall gamma 0 that's appearing in the equations of motion. But gamma 0 squared is invertible, so you can always just divide by it. So you can do either. Yeah. So for example, if we want the equation of motion, we can work out the equation of motion for psi bar. That's easy. You just cross off psi bar and it's this equals 0. That's the Dirac equation. Okay. So a few things to note. It's first order in derivatives rather than second order. That's kind of what's miraculous about it. The I here is just to make sure the whole thing is real. It's because if you integrate by parts, you pick up a minus sign, but then you want sort of the complex conjugate to... It's the same reason that the Hermitian operator in quantum mechanics is minus I times a derivative. Make sure the whole thing is real. The other thing to notice is it depends on m, not m squared. So m is again going to be the mass of the particle after we quantize. But notice that m here can actually be positive or negative. There's no requirement on the sign of this. So we'll find that after we quantize, it's the modulus of m that turns out to be the mass of the particle. Okay? But m can take either sign here. Okay, any questions? There's some cute notation that Feynman introduced. Anytime we have a vector, so any vector at all, a mu, and you contract it with the gamma matrices, so that what you end up with is a 4x4 matrix. You put a slash through it. So it's just some cute notation to stop you writing lots of gamma matrices everywhere. Okay. So this is a vector, just a normal vector. This is the set of 4x4 gamma matrices, and so this is then a 4x4 matrix, but a particular 4x4 matrix. So in particular, the Dirac equation in this notation reads the following. This is d mu gamma mu. Okay, so what I want to do today is tell you a few more properties about these Dirac spinors and the Dirac equation in general, and then maybe at the end of the day get on to quantizing the Dirac equation, but that may take until tomorrow. We'll see. Are there any questions about what we did before? Yeah, please. No implications of that at all. I think you could have just as well written a twiddle or anything else, but Feynman wanted a quick way to write this, and this is what he came up with. It's actually a bit annoying. Feynman didn't anticipate LaTeX, but in LaTeX, when you put this slash through something, it never quite sits where you want it to. So you have to spend ages moving the letter underneath a little bit to the right and a little bit up, just so it looks good. Is that right? Okay. Oh, I didn't know that. But to get this D slash in my lecture notes took me at least a morning, I think. figure out how to get that partial derivative under the slash. Okay, other questions? Okay, so I want to tell you about something called chiral spinors. And remember that for our particular choice of the gamma matrices, which we called the chiral representation. It's not the only choice, but it's the choice that we were playing with. When we worked out the Lorentz transformations that come from these gamma matrices, we found the following. So I think we got this in the last lecture. So this is for rotations. And this was for boosts. Okay, so you guys remember this? These were the things you act of psi with on the matrix indices of psi. So these are 4x4 matrices. We wrote them as the exponentiation of some infinitesimal generators. So these were e to the, there was no I because the generators were anti-emission, but they were e to the something times s mu nu, and the s mu nu's were the commutators of two gammas. Okay, so we ran through this calculation on Friday. On Friday, what I wanted to point out to you was that there's no factor of I here, which means that these guys aren't these guys aren't unitary, which in turn forced us to sort of define this new Dirac conjugate and jump through some hoops and put a gamma zero in the action. Okay, you remember this? This time I want to stress something else. These have come out to be block diagonal. Okay? And what that means is that we haven't found what's called an irreducible representation of the Lorentz group. We haven't found the smallest kind of representation possible, because if I just considered the 2x2 spinor here, instead of the full, sorry, not the 2x2, the 2 spinor instead of the full 4 spinor, if I act on that 2 spinor with either boosts or rotations, it doesn't mix into the other guy. It just stays amongst itself. Okay? So what that means is that this block and this block must themselves be a representation of the Lorentz group, and similarly this block and this block. So this is block diagonal. So this is a reducible representation of the Lorentz group. And it decomposes into two irreducible representations. Okay, so if we take our 4 spinor psi and write it in terms of two spinors. So this has 2 components, and this has each a 2-component spinor. And these have a name. These are called Weyl spinors. Eric, yeah.
You say that these gammas were the chiral representation and that it was irreducible?
Yes, so the gammas are an irreducible representation of the Clifford algebra. Okay, gamma mu equals Minkowski. But from the gammas, we then constructed a representation for the Lorentz group, and it turned out it was an irreducible representation. Sorry, it was a reducible representation of the Lorentz group. Okay, so this big guy is called a Dirac spinor. These little two-component objects, they're still complex. They're called Weyl spinors. They're sometimes called chiral spinors as well. So under rotations, well, we just read off from here. You can see that there's the same plus sign, so they both transform the same way under rotations. By the way, this is a 3-vector of numbers here, which is just saying rotate 16 degrees around the z-axis. Okay, but under boosts, they pick up a minus sign. More accurately, the transformation different by minus. Okay, so people know a lot of group theory. The U plus is sometimes called the half comma zero representation of the Lorentz group. The U minus is sometimes called the zero comma. Okay, good. So this Dirac spinor contains sort of constituent objects, U plus and U minus. We can look at the Dirac action. Okay, so this is the Dirac Lagrangian. If we write this out in terms of the U's, okay, this is psi bar. Okay, this is psi dagger, and psi bar is psi dagger times a gamma zero. So this is gamma zero. Okay. Okay, this is the Dirac operator d slash written out in full. Its derivatives d0. Maybe I should put d0 there instead of dt. d0 and the spatial derivatives di, multiplying the gamma matrices. Okay. And then there's a minus m, u plus u minus. Okay, so just writing this out and introducing a little bit of new notation. Okay, well, I've introduced a new notation which looks like the Pauli matrices, except now it's got a space-time mu index on instead of the I. And so this is a set of 4 2 by 2 vectors, 2 by 2 matrices. The first one is just the unit matrix. and the others are just the Pauli matrices. And this guy U bar here, the first one is the unit matrix, and the rest are minus the Pauli matrices. This is not the Hermitian conjugate of sigma. Okay, it's just some new notation that I've introduced, and it means this.
Is there a 4x4 matrix attached to M?
Yes, it comes with the unit 4x4 matrix. That's wherever there's an M in the Dirac equation, that's always implicit. And in this equation, it's not needed because this vector just contracts with this vector through this matrix. It's always. Okay, you guys happy? I just plug this in. So now we can see why the Dirac equation is something that's a little more useful than, at least at first sight, than the Weyl. Or the Dirac spinors are more useful than the Weyl spinors. It's because the Weyl spinors are 2x2 objects. They have their kinetic terms that sort of is a kinetic term for U minus and a kinetic term for U plus. But then if you want to add a mass, the mass necessarily couples U plus dagger to U minus. Okay. So for massive fermions, we need both U plus and U minus because they couple together. But if you have a massless fermion, that can be described by just a single Weyl spinor instead of two Weyl spinors. By the way, I guess the language here is anticipating what we're going to see, which is that when we quantize these spinor fields, we're going to get fermions. So I'm just using this language here. Okay, so if we have a massless spinor field that will give rise to a massless fermion, we can describe it, or such an object can be described by just a single Weyl spinor instead of a pair of Weyl spinors. A single Weyl spinor obeys the following equation. This is the equation of motion that comes from this action when m is 0. And you get it just by crossing off this. There's a similar one for U minus if you chose to describe a spinor by U minus. Okay? Okay. So just derivative equals 0, no master. Okay, so if we have a massive particle, it has to be described by a Dirac spinor. If there's a massless particle, the Dirac spinor decomposes into two objects, U plus and U minus, which don't talk to each other, at least at this free level. And so it may be that there are particles in nature which are just described by one of these objects and not by the other. I have a question for you guys. Who knows any particles in nature that are described by Weyl spinors of this type? Neutrinos, good. Does anybody know of any others?
But neutrinos are massless.
They're not, no. Does anybody know of any others? No? Okay. Every particle in the standard model is described by Weyl spinors of this type instead of Dirac spinors. Okay. And as you pointed out, the neutrinos aren't massless, and neither is anything else. So what's going on? Well, all of the particles in the Lagrangian we write down in the Standard Model are massless. There's never any mass terms of this type here. They get their mass through another mechanism called the Higgs mechanism. And you'll learn about this, I don't know, maybe in the next course, maybe in Michael Peskin's Standard Model course. But in particular, because of the weak force, all the fermions in the Standard Model have to be described by Weyl spinors or chiral spinors. And they come in pairs for all the fermions. So there's a U plus for a fermion and a U minus for a fermion, but those have different properties, the U plus and the U minus. So they can't be combined together into a Dirac spinor. Okay? And you'll learn about this later. But everything is massless in the Standard Model. Yeah.
Now that we're talking about interpretation of it, how do we interpret this U plus and C minus, and then how do we interpret this U plus and minus? And I know we're about to talk about
Yeah, I wasn't actually going to talk about it.
Okay. So there's two here, I guess, since they're massless. But yeah, what's going on here physically?
So physically, what's going on, it's probably best described in terms of particles instead of fields. So when we come to quantize these objects, we'll find that the particles we're getting have extra internal degrees of freedom. That we'll interpret in terms of spin, and that there'll be spin up and spin down for certain particles, and there'll be particles and antiparticles.
So this U plus field which gives rise to particles.
Yeah, but we're actually going to quantize the psi. We're going to quantize massive guys, quantize the field psi. This fact that it's U plus and U minus that are important will be fleshed out in our quantities.
That makes sense.
But we'll quantize the psi. We'll find that it's complex. It gives rise to a particle and an antiparticle. And each of those particles is spin half, which means that it can be spin up and spin down.
That's what it is.
So that's sort of the physical interpretation of this extra index is telling you. Other questions? Okay. Okay, a little bit more Diracology. I'm going to tell you about gamma 5. Okay, so what's the right way to phrase this? Here we wrote down that psi was just U plus and U minus. Two components at the top, two components at the bottom. But if you trace back why that was sensible, it was sensible because our particular choice of gamma matrices, that chiral representation, which then gave rise to that particular choice of Lorentz transformations that was block diagonal, so it made sense to have U plus at the top and U minus at the bottom. Okay? But if for some reason I want to work with a different set of gamma matrices, my Lorentz transformations are not going to be block diagonal, and everything's kind of all going to be mixed up. So there's still lurking inside there two spinors, U plus and U minus, but they don't just sit naturally up here and naturally down there. They're all sort of mixed in some complicated way within this four vector. Okay? So what I want to do now is just explain to you how you think about these Weyl spinors in any arbitrary gamma matrix basis. Okay? And we'll introduce this thing called gamma 5. Okay. So we introduce a fifth gamma matrix. And we get this just by taking all the four gamma matrices and multiplying them together. Okay? It's dead easy. So you can convince yourself that this has certain properties. Firstly, it anti-commutes with the first 4 gamma matrices that we came up with. And secondly, it squares to 1. Okay, so it really is the, sorry, I missed a 5 there. Gamma 5 squared equals 1. Okay, so you can check both of these just on the definitions of the other gamma matrices. You don't have to plug in explicit gamma matrices here, but just the fact they obey the Clifford algebra guarantees that this is true. Okay, so it's a 5th gamma matrix. We call it gamma 5. You might think gamma 4 is sort of more sensible, given that the others are gamma 0, 1, 2, 3, but everybody calls it gamma 5. Okay? But one reason is that often we want to work in Euclidean space, where the mu label goes from 1 to 4 instead of 0 to 3. And so there it makes sense to call it gamma 5. It just sticks. Okay, so what to say here? Given 4 gamma matrices, we get a 5th for free. It's clear that now gamma 5 and the gamma mu's satisfy a Clifford algebra that's in 5 dimensions instead of 4 dimensions. Okay? Gamma 5 anti-commutes with everything else and squares to 1. This is something that holds in all even dimensions. So if you take that Clifford algebra, you try to figure out gamma matrices that obey it in any dimension. If the dimension you're in is even, you can always just multiply all your gamma matrices together and pick up an extra gamma matrix that obeys the Clifford algebra in 1 dimension higher. Okay? Okay, now the crucial point is that back in 4 dimensions, this guy squares to 1. So since gamma 5 squared equals 1, we can define a projection operator Okay, this is a Lorentz invariant way to describe a projection onto a 4-component Dirac spin. Okay. So in particular, once we've got a projection operator, there's 2 projection operators, p plus and p minus. Each of them projects onto half the vector space spanned by psi. So we define chiral spinners as just taking a usual Dirac spinner and hitting it with this projection matrix, p plus minus. Okay? It's going to project out half the degrees of freedom of this. You're left with something that's psi plus minus. And this guy here is the analogous thing to the Weyl spinners, u plus minus, but in an arbitrary basis. Okay? In particular, if you went through this procedure in the chiral representation and figured out what these psi plus minus were, you would find in the chiral representation, we find psi plus is u plus 0, and psi minus is 0 u minus. Okay, is this clear? So one reason to tell you all this is, in the last lecture I worked very hard to try and come up with objects which were scalars under the Lorentz group. So you start with psi, which is a spinor, and you want to construct something that's a scalar. And we learned that the thing to do is to do psi bar psi. Psi dagger psi didn't do it, but psi bar psi did. Well, we've got this new matrix gamma 5, and you can show the psi bar gamma 5 psi is a Lorentz scalar. Actually, there's an extra word you should add here, which is pseudo scalar. I'll explain this in a minute. It's a Lorentz vector, and I think it's called the same thing, a pseudo vector, axial vector. That's it. Okay, so we have a spinor field. We want to start writing down Lagrangians, which describe interactions, perhaps with other fields. What we have to play with are basically the sensible objects we can construct out of psi. So we can construct psi bar psi, but we can also put a gamma 5 in between there. And that's also something else we can write down in a Lagrangian. Okay? And the same for this vector interaction. These words pseudo, I'm not going to describe to you in detail what these mean, because I think Michael Peskin's going to do it in the standard model course. If he doesn't, you should bug him and make him. It's all in the notes if people want to read it before time. But this basically means how these things transform under parity. So there's this extra discrete symmetry, which your theory may or may not have, which is basically what happens if you flip the theory and look at it in a mirror. And you can show that this picks up a minus sign under that, and this also picks up a minus sign under that. So that's what this pseudo and an axial mean here. So in general, if you see a Lagrangian with a gamma 5 sitting in there, that's an example of a theory that looks different in the mirror than it does not in the mirror. Okay? So this is just sort of giving you a nod for things that will come up in the standard model. Okay, any questions about this? I'm flying through kind of quick and just giving you the basics, Eric. Yeah.
How come how do the projection operators do this? How come it works?
Did they give this?
Yeah.
Yeah, for that particular case, you actually have to figure out what gamma 5, what this is. So if you plug in the specific gamma matrices in the chiral representation, what you get is that it's equal to this. This is the 2 by 2 unit matrix here and here. So that when you form the projection operator, the projection was the top bit or the bottom bit. U plus U minus. I may have mixed a minus. I don't know what's going. It's right. Okay, other questions? So there's this whole story about sort of substructure within the Dirac equation. There's something else called Majorana spinors, which is a way to make the Dirac spinor, which is 4 components, real instead of complex. Again, there's a page in the notes about it. You may or may not come across this in the standard model course. But I just want to move on. I don't really want to dwell on this. What we're going to do when we come to quantize is just consider the Dirac spinor. We won't be thinking about these Weyl spinors at all. Okay. Questions? Okay, let's look at the symmetries of the Dirac equation. Okay, so there's a bunch of symmetries that this Lagrangian has. The first 2 are the ones that we've seen already for the scalar field. It's the fact that it's invariant under space-time translations and also invariant under 6 Lorentz transformations. So each of those is going to give rise to a conserved current or a bunch of conserved currents for this Lagrangian. So instead of deriving them, and if you want, you can sit down and do them. You know, it's the same sort of techniques we were thinking about in the first week. I'll just tell you what they are. So translations, we get the stress energy tensor. And it's equal to the following. Okay, so this is just applying Noether's theorem for this particular symmetry to this Lagrangian. For Lorentz transformations, there is something kind of interesting, a new subtlety that comes out here. See, under a Lorentz transformation, psi alpha does the following. So we've already seen for a scalar field, we have transformations like this. That is just a transformation of space. And that gave rise to a conserved current that was angular momentum and this kind of weird thing for boosts. So the set of currents okay, so I'm going to use this notation that we've come across before. This is the current, and this labels which particular Lorentz transformation we're doing that gives rise to this conserved current. And so these are antisymmetric in rho and sigma. And it's equal to this x times the stress energy tensor which is the same thing we saw for the scalar field. But there's an extra term. And I've lost the extra term. Oh, it's here. Okay. And we pick up an extra term precisely because we were doing an extra thing when we did a Lorentz transformation. So this bit here contributes this to the conserved current. Okay, this is important for the following reason. When we quantized the scalar field, I said that to understand what we call the spin of the scalar field, it's nothing more than how things change under rotations. So in that case, what you do is you compute the conserved quantity due to rotations. That looks something like this. You then turn that into an operator, and you act with that operator on the state that corresponds to a stationary particle sitting here, and it gave 0. Okay. We'll do exactly the same thing here when we quantize. We'll quantize the Fermi field. We'll act with this operator on a single particle state that isn't moving, but we'll find it gives a half, and it gives a half because of this term here. So this term here is what's telling us that these particles are spin half after we quantize. Okay. Yeah, please.
Would never have appeared in the scalar.
No, the scalar didn't have this. Just transformed here. So if you like, this transformation is given these two terms, and it's this extra bit which is given you. There is a similar term if we consider vector fields, because they also transform. Other questions? Okay, there's a couple of internal symmetries. So one is just the fact that psi is complex. We can change the phase of psi. This action doesn't change. Okay? This doesn't depend on space. This is just an overall constant change of psi. This has a current associated to it, sometimes called the vector current, for a reason I'll describe shortly. So there's a V for vector. And it's just equal to psi bar gamma mu psi. Okay. There's a conserved quantity associated to this. You take J0, you integrate it over all of space. That's the conserved quantity that's going to tell us particle number for fermions. Number of particles minus number of antiparticles. It'll also be electric charge and things like this when we come to introduce electric charge. And finally, there's one extra symmetry which maybe isn't obvious. If the mass is equal to 0, so this term isn't here, then, you know, we already saw, we expanded this action out in terms of U plus and U minus. And if the mass isn't 0, sorry, if the mass is 0, then there's nothing coupling U plus to U minus, which means I could change the phase of U plus by something and change the phase of U minus by something else, and that's still a symmetry. Okay? That's only true if M is 0. So you can check there's a nice way of writing this in terms of this gamma 5 matrix. Okay, so what this gamma 5 in this exponent is doing is it's making U plus transform as e to the I alpha and U minus transform as e to the minus I alpha if we're in the chiral representation. But this has the advantage that it holds for any gamma matrices at all. Okay? Okay, so we get a new symmetry where you just put a gamma 5 in here. Again, this is only a symmetry, only a conserved current for massless fermions, not for massive fermions. Okay, there's actually a beautiful story to do with this symmetry, which you'll come across maybe in the standard model or maybe in the next quantum field theory course. This is a symmetry of the classical theory, and it doesn't survive to the quantum theory. So it's an example of what's called an anomaly. You think when you look at your equations that you have a symmetry, but actually it's not there. And it's a wonderful, it's really one of the most beautiful things in quantum field theory. And it's all to do with these infinities and how you deal with the infinities. And basically what happens is that you need to find a way to get rid of the infinities, but every way you can think of that gets rid of the infinities breaks this symmetry. Sort of has to introduce a mass somewhere along the lines. And it's not recovered at the end of the day. And this is important. This actually happens in nature. Nature would be very different if this symmetry existed than it is today.
But if things are massless in the same model,
then why don't we still have that symmetry?
Right, so this symmetry is there in the classical theory. But when you come to quantize, the symmetry in the classical theory doesn't survive through to the quantum theory.
But, so that even if m is 0, is that?
Even if m is 0,
okay.
Yeah, the symmetry is only there in the classical theory when m is 0. And the statement is that it's never there in the quantum theory.
I see, I misunderstood your story.
Yeah. We're getting ahead of ourselves. Yeah, please.
If we have near fermions, then fermion number is not necessarily conserved.
Yeah.
So how does that But I mean, here we would still have the same symmetry, would still have the same conserved cube.
No, the Majorana fermion is such that this is basically a real object.
Okay.
Suitably so. And then just like for a real scalar field, you can't do this. There's actually another basis of gamma matrices in which you can just make psi real and then call it a Majorana fermion. Whereas it's a bit like the introduction to gamma phi. If you're at an arbitrary basis of gamma matrices, you have to work a bit harder to say what you mean by this being real. You can't just set it. Other questions? Okay. I think this is one of the most boring lectures. Let me quickly move on and tell you about the simple solutions to the Dirac equation. Okay, we would just want to solve this equation. Did Malcolm tell you about solutions to this equation? No? Oh, by the way, one thing I told you, I didn't tell you, but Malcolm did. This equation sort of mixes up all the different components of psi here, because there's a gamma matrix just here. There's a way to act on the left here with basically I gamma mu d mu plus m. And if you do that, you find that each individual component of psi solves the Klein-Gordon equation. So I think Malcolm did that calculation with you. Is that right? And usually people say that that's the proof that this is a Lorentz invariant equation. I think that's even how Dirac wrote down this equation to begin with. I don't think that's quite true. Of course, it is a Lorentz invariant equation, so it's hard to say what the proof is. But I think the proof is what we did, of going through and showing that this transforms as a Lorentz vector, this is a Lorentz scalar, and so on. Okay, so a couple of different solutions. One's called positive frequency and one's called negative frequency. Okay, this is some full vector for spinor. Let me look for solutions which are of the form e to the I p dot x, where this is a particular fixed for spinor, which is going to depend on which p I'm looking at. Okay. So the solution to the Dirac equation with this ansatz is the following. Okay, so what do I mean by this? P is the particular four momentum that is part of the ansatz of the solution. Okay, it'll turn out to be four momentum when we quantize, and here you can sort of see it already because it's a Fourier transform. Okay, this is a four momentum, and it's dotted with these particular four 2x2 matrices. These are the sigma mu's that I described earlier. So P0 is dotted with the unit matrix, and then the PIs are dotted with the Pauli matrices. Okay. The same here, but there's that extra minus sign because these are sigma bars, not sigmas. Proof of this I'm just going to leave as an exercise for you to do this afternoon. You're going to have lots of exercises this afternoon just playing around with gamma matrices and just getting used to them. Okay? But it should be clear. You take this, you put it in here, you plug the whole thing into here, and you show that that this solves the Dirac equation. Where are their squiggles? Oh, good. Sorry. So yeah, these are Greek letters called xi, and each one is a particular two-component complex spinor. Okay, and it can be anything you like. It has to be the same, but other than that, it's anything you like. So in fact, it's often useful to introduce a basis.
We're calling it UP. Does that
We-
mean that it's one of the V?
Sorry, say again?
If we're calling it UP, that would,
Yeah, it's just a name. It's going to come up later in the course. It's a particular four-dimensional. It's a particular four spinor that takes this form that depends on P. Oh, by the way, P0 here is always taken to be the square root of P squared plus M squared. Okay. The xi is any two-component spinor, and it's going to be useful later on to introduce a basis of two-component spinors. So I'm going to call them f equals 1 and 2. This isn't the spinor index. This is just telling me which particular spinor I'm interested in. And I just want them to solve the following equation, that it's basically a basis, that their inner product with themselves is 1 and they're orthogonal to each other. Yeah. Yeah. Do you know, I think we almost certainly have, right? Otherwise, yeah. Solution, yeah, in the chiral representation. Yeah, it has to be, otherwise there's not enough information there. But yeah, thanks. That's important. Okay, so here's just a simple example of a basis that you probably should have in mind when playing with this. Okay, so that's two solutions to the Dirac equation. Two because this is a two-component spinor here, and we can either have this guy or this guy. Okay. So the other solutions are the negative frequency solutions. And these take the form where you try and put a plus sign here instead of a minus sign. Sorry, I should stress here. The reason that this isn't the same as this, where you just send p to minus p, is because p0 here is not something arbitrary. Right? It's fixed to be this odd shell guy. I guess when you do this exercise, you'll see that that's the case. Sorry, I should have stressed that. Okay. okay, this afternoon you're going to do this exercise, you're going to do this exercise. These etas are again two-component spinners, any two-component spinners, but the same one. And you'll check that this indeed solves the Dirac equation. You'll also do a bunch of other exercises to do with when you take the inner product of one of these with itself, or one of these with one of these, or the outer product, and there's all sorts of identities that these guys satisfy, and you're going to just prove them all this afternoon because they're going to be useful later. Joe, you had a question? No? Oh, you sort of put your hands up. You, okay, any questions? Yeah.
For the negative frequency solutions, is P0 the negative square root?
No, P0 is still the positive square root. Okay. So sorry, this is a bit muddled, and I keep remembering extra things to tell you. And I usually go through this on the board, we just don't have time, so that's fine. Remembering what I've forgotten to say. Okay, is this all clear?
With the single under it, so you wrote, well, you wrote one in this photo there, and you wrote one up there. Do you mean the same thing?
I mean the same thing. This is a vector, or a four-component spinner. It depends on the value of 3 momentum p in Helix. So that's really what this means. It's just telling you that it depends on p. And the reason it doesn't depend on p0 is basically because p0 is fixed.
Okay, so, right.
Yeah.
That's also a spinner up there?
No, good. So this is, these are just the 3 numbers, and p0 is the 4.
Okay,
So this is just, an usual e to the IPX, the same kind of e to the IPX we have for the scale. This is the 4-component object. And it's given by this. This in itself maybe takes some explanation, because this is a 2x2 matrix. And then you take the square root of the 2x2 matrix, which basically means you need to find a matrix which squares to that 2x2 matrix. And then you act on this arbitrary 2-component spinner. Yeah, it'll be clearer this afternoon when you actually sit down and show why this is the solution. But I need this notation for what's coming up. This U and this V are going to be important. Okay. Other questions?
Oh, there was a square root.
Oh, sorry. No, it's a V.
Okay, yeah.
Yeah, okay, that makes sense. It's supposed to be U. Yeah, okay, sorry. Okay. You'll be pleased to know we're just fitting into one lecture something that took 2 lectures to master this course. Because of Thanksgiving. Any questions about this? No, it's fairly straightforward, but I appreciate you probably just have to sit down and do the algebra to really see what's going on. Okay, so now we're going to move on, and we're going to quantize this field. Okay, and what we're going to do is do exactly the same thing as we did for the scalar field, okay? Except that's going to be the wrong thing to do. But I want to sort of do the wrong thing, the naive thing, lead you through it, show you where it goes wrong, and then tell you how you rescue things, okay? So this is the action. The first thing to do is just think of this as a classical theory and figure out what the momentum is that's conjugate to psi. So the momentum is defined by the derivative of the Lagrangian with respect to psi dot. Differentiate with respect to psi dot. There's the I, there's a gamma 0 lurking in this d slash, and there's the psi bar. Okay, but psi bar gamma 0, we have a name for that. That's just psi dagger. Okay, so what to say here? Firstly, notice that the momentum isn't proportional to something dot, so this might be a little unfamiliar. This follows immediately because we've got a first order equation of motion here rather than a second order equation of motion. Okay. What this means is, and this is a statement just within the classical theory, just theories of differential equations. For a classical field, if you want to know how it's going to evolve for all times in the future, you have to stipulate what the initial data of the field is and what its initial velocity is. Okay, two initial conditions, second order differential equation, then you know what happens from then on. Here that's not true, that you need to specify the correct statement is that you need to specify the field and its momentum, but we see now that the momentum is just the conjugate of the field. Okay? So the initial data you need to specify is psi as a complex field at the initial slice, and then this first order equation takes you on over from there. Okay. So we'll proceed as we did for the scalar field. And we'll see that this will actually be the wrong thing to do. Okay, so what do we do for the scalar field? We have a field, which is a function of space and time, and we have a momentum, which is a function of space and time. And what we did for the scalar field was we imposed canonical commutation relations between position and momentum, field and itself. Okay? We first are going to work in the Schrödinger picture instead of the Heisenberg picture. So now in the quantum theory, psi and pi become functions just of space and not of space-time. We'll go to the Heisenberg picture later. Okay. So impose canonical commutation relations. Okay. All of these are three vectors, and they're three vectors because we're in the Schrödinger picture. Okay. You could have these spinor indices up or down. It doesn't matter. We're not going to raise and lower them with any metric. Okay. Okay. So this would be our first guess. One small point, there's no factor of I here, and that's because there's an I inside the momentum, so it's just cancelled. Okay. It's going to be this very first step that we've done wrong already. But I'm just going to push through to show you why it's wrong. Okay. So we need a mode expansion. For these fields, psi. Again, just as we did for the scalar field, we expanded in terms of creation and annihilation operators. We'll do the same here. Tell me. Are you sure? You want to just, will you still copy?
Yeah.
Okay, so the mode expansion is the same conceptual idea we had before, but it's just going to be a bit longer. It's going to be a bit longer precisely because we've got these spinor indices to play with. Okay. Okay, so what's going on here? This is an operator, but there's an alpha index that I've suppressed. So really, it's 4 operators in a spin. Okay, that's what this guy is. This is doing basically the mode expansion or Fourier transform of that operator. And yeah, thanks. Yeah, that's right. Okay, so this is familiar. This is familiar. These B's and C's are operators. Okay. And we've introduced 2 operators here and 2 operators here. Okay, different operators, B and C, just like for the complex field, not like for the real field. These guys here are spinors. So it's these that are soaking up the spinor index of this. And these are exactly the spinors that we've seen already, where the S index is the index on this basis for P dot sigma bar zeta S. Okay, so the S index is the index on the basis for these 2 component objects, 1, 0, and 0, 1, basically. Make sure I got the minus signs right there. You good? Okay, so this again is an operator, but it's a bunch of operators sort of as a conjugate vector, so going this way, and similarly these guys go this way and these guys go this way. But these are just the operators. Okay, so by playing around with these S indices, we sort of absorbed we basically wrote down a basis of spinors, labeled that basis by S, well, by U and by V, and then by S, and then absorbed that S into the operators. Questions? Yeah.
You're taking the adjoint.
Yeah, good. So these and these compute. Yeah, the answer is yes. They sort of live in different spaces.
Yeah, but we don't really know much about those coefficients yet. So can
This is just it's just a matrix. Sorry, a vector of numbers. It hasn't been turned into an operator. It's the coefficients here that are turned into operators.
right.
So these are operators, but these aren't. They're just the same things we have here.
What do the operators B and C act upon?
It's the same issue that we had in the scalar field theory. We're going to construct a Fock space.
Okay, so they act.
Yeah, they're going to be, again, creation and annihilation operators.
Okay.
For objects in a Fock space. Questions? No, is the notation clear? The notation not clear. Eric, you almost raised your hand.
I just was going to ask, when these B's and C's operate, do we operate them as two-component operators, or do we operate them independently, like the?
So there's two B's, B1 and B2, and you could just think of them as two different creation and annihilation things, and the same for the C's.
Do we use them independently, or do we always have to use both at the same time?
No, we use them independently. You have the vacuum you can activate either with B1 or with B2. The interpretation is going to be that these are creating a particle that spin up. Okay, that's what we're looking at. Other questions? Good. Let me just tell you what goes wrong with this theory. So we do the same thing we did before. We have commutation relations between these, and they imply commutation relations between B's and C's. I think this goes somewhere towards answering your question. There's an R and an S index there, and there's just delta RS. So you act with one or the other one. Then they commute with each other. Okay. So the proof of this is an exercise for you guys, and you're used to these exercises now, right? You know, just plug it in. Do Fourier transforms and then commutations, and then Fourier transforms and then commutations, and then out. There's a minus. Okay. Nothing wrong with it at the moment, but it's different from the B's, and it's different from what we had for the scalar. There's a minus. You know, you might think that's okay. We'll just redefine C and C. There's a minus. What's the next step? The next step that we did was to look at the Hamiltonian. By the way, when you do this exercise, you'll need to know some of the Q properties of those U's and V's, and you'll figure out those Q properties and so on. There's things like sweeping under the rug. nothing different about the Hamiltonian. It's this. Again, this is purely classically. You plug in the definition of the momentum, which is just psi dagger. Notice that the time derivative disappears completely from the Hamiltonian. Okay? This is something that happens whenever you have first order equations of motion. Because this is pi psi dot, but when you take off what's here, there's already a pi psi dot. So when you get to something with no, it doesn't depend on time derivatives. Okay. So again, these kind of tedious things where you've got H in terms of some fields, but you now plug in the operator expressions for the fields, and you put H is as an operator. It's just right here. The actual Hamiltonian. Of course, that's the integral of the Hamiltonian density. Okay, so we do the same thing we did for the scalar field. This is the Hamiltonian. There's a sum over S equals 1 and 2. So you sum over the all the creation and annihilation operators. There's 2 for B and there's 2 for C. And the problem is that there's a minus sign just here.
That sounds stupid, but why is that a problem?
This is a problem for the following reason. This theory doesn't make any sense because it has no stable ground state. Okay? You define a vacuum which is annihilated by B and C, but then if you act on it with C dagger, you're going to find a state with lower energy because of this minus. And you can keep going and keep going. Now, we've come across infinite energies before, so you might think, well, there was that normal ordering coefficient, maybe I can help make that work for me. You might think that you can go back to the original definitions of C's and try and change them. But this minus sign is like a bubble in wallpaper. No matter how you try to fix it, if you change something, it just reappears. Okay? This minus sign is a real problem.
I wasn't bad, I just didn't see this.
So the energies are unbounded below. So in fact, there's no way to make sense of spinor fields quantized in this way. So if you start with those initial commutation relations between psi and psi dagger, you'll always screw up. You'll never get a sense of it. Yeah.
Is this at all related to the idea of like a sea of particles and antiparticles that have like infinitely low energies, and then to get a particle you sort of just pop one out?
Right, so Dirac found something very similar in his interpretation of the Dirac equation. That interpretation is not, that interpretation that Dirac postulated was treating psi as a wave function for a single particle. And that's definitely not what it is. So yes, it's the same sort of idea. I think in the next lecture we'll see the resolutions of this. And I may also just sort of compare and contrast with Dirac's picture. Let me just finish the sentence here, and then I'll come back to you. So we can't make sense of spinor fields quantized in this way. And what we've got to change is that we've got to treat them as fermions. And that means going right back to those commutation relations we started with and writing down something a little bit different. And we'll see exactly what it is in the next lecture. But what you're seeing here is the first glimpse of what's called the spin statistics theorem in quantum field theory. You know that half-integer objects are fermions and integer spin objects are bosons. What we're seeing is if you try to take a half-integer spin object, the spinor, and quantize it as a boson, you don't get anything sensible. And the only way we're going to get anything sensible, for example, having energies that are bounded below, is to quantize it as a fermion, which we'll do in the next lecture. Eric, you had a question?
Oh yeah. So when Dirac did all this, did he know about spinners?
He sort of invented it.
Well, when he postulated the Dirac equation, because okay.
That was psi. That was his.
Yeah.
Other questions?
So also on a historical point, did he know about fermions? I mean, did we get to fermions before we got to the Dirac equation, and then he said, oh well, he saw this, and then said, oh well, this must be a fermion, or which way around?
His solution to this was that there was an unbounded spectrum, and he said, but they're fermions, which is something extra you have to throw in by hand. And then he says, well, they're all filled up, and all the states are filled up. And we start there. That's not really the right interpretation. It's a very useful interpretation, especially as it's exactly the right interpretation in condensed matter physics, where you talk about the Fermi sea instead of the Dirac. But it really comes from thinking of the Dirac equation, the psi being the wave function for a single particle. That's when you run into these problems, and that's not what it is. And I'll try and elaborate on this.
So that's just the number operator, pretty much, right? The
Yeah.
B. So it's just the difference in particle minus any particle.
That's what it looks like. Yeah.
Yeah.
Exactly.
So
It's not. It's the energy of the universe.
yeah. But can the energy of the universe just be the difference between particles and antiparticles, like particles and antiparticles?
But then you
cancel each other out, right? Oh, but you can still just keep making it.
start tumbling down.
Yeah. Right, and you eventually get negative energies. Yeah.
What if antiparticles have negative energy?
Well, yeah, that's.
Then that would be a theory that was unstable. You would
So
just
yeah,
keep creating
still just add a
antiparticles.
bunch of antiparticles.
This is
eventually
basically
get
what this
negative
is.
energy.
Okay.
But this is saved. And the theory doesn't make sense. And it makes sense on the free level, because basically on the free level, you put particles there and then they rotate. So it's only when we come to consider interactions that every interaction will start creating as many antiparticles as it could. So it will be radically incompatible. Other questions? Okay, let's do coffee.